chapter 9. So, last time we finished chapter 4. Today we are going to start chapter 9. In chapter 9, we are going to address the phase diagrams. Before we do that, let's look at this in order to have like the motivation into this chapter, why we are going in this direction. You remember before we start, you're listening, right?
اي دكتور.
واضح كل شيء. لأن اليوم في ظهر شو اسمه فيرجن أو أبديت صار كما اشكرت لما دشيت طلب مني شيء ثاني ف I was just checking. Hopefully this will be recording normally also. So before we go into the thrust of phase diagrams, you remember this figure that we have seen before. This figure, let me use the laser pointer bigger. So we remember the relationship between the structure, properties, and the process. We said we can do different processes there in order to change the structure of the material, which inevitably is going to change the properties of the material. These processes could be bending, as you could see there. This is the sheet which is being bent. You have a change in mechanical working on the material here, which changes the structure and therefore changes the property of the material. Drawing, for example, as you could see, it's changing the structure of the material. The grains are changed, and that's why you will have more dislocations develop in the material. Material will become stronger. You could have deep drawing, and this is a sheet which you have. You deep draw it like that, like development of cans, for example. You would be changing the structure of the material. This is a stamping, if you remember what the stamping is. These are all mechanical drawing again here, which is the same as that. You have a drawing here. These are all mechanical processes which would be used in order to change the structure and therefore change the properties of the material. Hot forging, this is another. So this is the forging, for example. We could have also chemical processes such as the alloying. You could be alloying a material with another material. So also here, this is a process which will change the structure of the material, obviously, and therefore you will change the properties of the material. Heat treatment. This is a furnace, a big furnace in industry. These are heat treated specimens there. You can heat treat the material in order to change the structure of the material and therefore change the properties of the material. Now, in this chapter, phase diagram, and the next chapter, we will be focusing on two issues: the heat treatment and basically the alloying as well. So we will see how is the composition and the heat treatment of the material using the phase diagram changes the structure of the material and therefore changes the properties of the material. We will have what we refer to as the phase diagrams. The issues that we are going to address, that when we combine two elements in an alloy, so if we are doing the alloying, we have a mother material, we add another material. We have copper, we add, for example, zinc to it. We have iron, we add whatever alloying element in it. In particular, at a composition, at a certain composition, let's say weight percentage of copper and nickel at a certain composition, and a specific temperature, we will be answering important questions, and we will see why these are important questions towards the end of this lecture. How many phases do we get from that composition from the alloying that we are doing and at that temperature that we are having? How many phases are we going to get? What phases are we going to develop in the material? What is the composition of each phase that we are developing, and how many of each phase we are going to get? Basically, this is what we are looking at. Are we going to get one phase? Are we going to get two phases, like phase 1 and phase 2 in the material? Because it differs. If you have different phases. Different phases will have different crystal structures, and different crystal structure will have different crystal structures will have different strength. So even in a phase itself, what's the composition of that? Because even the composition from in the same phase, if the composition is different, also the material behavior will be different as well. So these are the four main questions that we are going to answer using the phase diagrams, basically. So this is what we are going to do in this chapter. We are going to use the phase diagram. Of course, we are going to first of all learn what phase diagram is, and we will use the phase diagram as a tool in order to answer these important questions. We will shed light more in detail on why these four aspects are important in any structure or microstructure of material. We will be shedding light more as we go in the thrust of the phase diagrams. So the phase diagrams are basically tools that we can use, adawat that we can use to predict the material microstructure or the material properties. This is what we normally do and use the phase diagram. We will see as we go. So why phase diagrams are important? The phase diagram is an important tool for material scientists and engineers. A phase diagram can be used to predict the equilibrium compositions and proportion of the phases in a material for a given chemical composition and particular temperature. So if we have the temperature and we have the chemical composition, we can use the phase diagram to predict the equilibrium compositions and proportions of the material. Yani, if we have the phase diagram, we can predict how many phases we are going to get, what these phases will be, what is the composition of each phase, and what are the proportions of each phase. Yani, two phases, for example, how much percentage is this phase and how much percentage is this phase. You can also predict that, because that is an important issue as well in predicting the properties of the material. A material, this is what we are saying again, a material microstructure can be predicted using information from the phase diagram. But one important thing that we need to also realize here, the phase diagram alone cannot serve and cannot make you understand or cannot make you predict what we are saying here, except that you should be knowing the processing route. Processing route يعني شنو؟ Processing route means the heat treatment history. يعني the history من مالت المعالجة الحرارية اللي قاعد تسويها. What is the history? Did you quench? Did you anneal? Did you normalize? Did you slowly مثلا did you normalize? There is a mixed type of heat treatment route that you are following. That heat treatment route needs to be known in addition with the phase diagram in order to be able to predict the compositions and proportions of the phases which are going to get produced by the treatment that we are having. So both of them need to be known: phase diagram and heat treatment history. And why am I insisting on saying that? Because this is normal. Because this is what we are saying, knowing the chemical composition and particular temperature. Not only knowing that particular temperature we are at, but knowing what happened before that. Yani, where were you and how did you cool down? This is the history which we mean. يعني الطالب راح يصح، الطالب وصل الصف. اوكي، الطالب وصل الصف وانا عندي ايش اسمه, this is his history. No, his history, how did he come to the class? He went to the gate of UOB, and then he went to the cafeteria, and then after the cafeteria he went to Madri Wayne, and then to building 15, and then he came to our class in building 14. مثلا, you need to know the history, the route that he followed. The same thing which with us in the phase diagram, we need to know the history of heat treatment in order for us to be able to know the structure of the material. For example, somebody shows me a structure of the material. This is can you tell me what this is structure? What, for example, I know it is steel. Can you tell me what the structure of the material is this? Just like that, without telling me the heat treatment history, the processing route that he went through, I wouldn't know. Nobody would know. But if we are given the history of heat treatment, then I can use the phase diagram to know what phases you have in particular in that figure that you're showing me. But if you just tell me we are at this temperature and we are at this composition, what is this phase that we are having? I wouldn't know from just looking at the picture. So this is something which I wanted to be clear about. Next, a correlation exists between microstructure and mechanical properties. So that is that been saying long term. Structure and properties are strongly correlated. So obviously, if you can, and this is what we are saying, thus the mechanical behavior or properties of a material can be predicted from the phase diagram. So if we can use the phase diagram to predict the microstructure that we have at a certain chemical composition and particular temperature, therefore, if we know the structure, we would know what the properties of the material is, because we know that correlation. We know that there is a relation between the structure and the properties of the material. As we go, we are going to learn more how to predict that. Before we go in the thrust of the phase diagrams, there are some basic definitions or basic concepts that we need to go through first of all before we start looking at the phase diagram. Simple basic concepts. First of all, we will be using the word components, as in your book as well. As you read, you will see the word components are used. Components, for example, let's say brass. If you remember, brass consists of two components: the copper and the zinc. This is how it is used. So the components of the brass are the copper and zinc. As simple as that. And the word system, when we refer to the word system, for example, when we say the steel system or the iron carbon system, which has two components, basically iron and carbon. You have the brass system, which consists of two components, which are the copper and zinc. As simple as that. So when you hear components, you now understand that it's the components of a system. And what is a system? A system of alloying materials together. This is called, for example, a system. Phases. What do we mean by a phase? A phase is a homogeneous part of the system with uniform physical and chemical characteristics. At this here, this is a phase. This is another phase, for example. Of course, this we might say this is a third phase. Anyways, if it is different than this one, of course. A phase is a homogeneous entity which has a specific crystal structure throughout of it, or crystal structure or atomic arrangement, you can say that. It can clearly be separated from its surrounding. It has a specific mechanical and physical properties different than the rest, and it can be, easily also separated from the surrounding. So and it has a clear boundary between it and the surrounding as well. This is what a phase is. This is one phase. This is another phase. Here we could have, for example, a BCC crystal structure. Here we could have an FCC crystal structure, for example. These two crystal structures are different. This is atomic arrangement in them is different. Mechanical and chemical properties of these two phases are different. They can be easily separated from the surrounding by the boundaries that we could see. This is what we mean by in the material. Again, we will come back also after two slides to the phases. just to review more. We also covered previously in chapter 3 or 4 the solid solution. So we reviewed, we will have a small review now. So we have the solute اللي هو المذيب المذاب sorry المذاب the solute, and we have the solvent اللي هو المذيب المذيب والمذاب. We have the substitutional and interstitial solid solutions, which we have seen previously. So solid solution has two types, which are the substitutional solid solution and the interstitial solid solution. In the substitutional solid solution, and the solute atoms which are added substitute the solvent atoms. Substitute يعني شنو؟ يعني تاخذ مكانها المدير راح يجازه مثل ما قلنا ياخذ مكان المدير. So it's substitute. This is the word we're coming, and that's why in order to have a substitutional solid solution, this atom, the solute atom, has to have يعني conditions يعني for having a substitutional solid solution. The atomic size factor, for example, has to be atom sizes have to be يعني close to each other. They have to have the same crystal structure type. They have to have the same energy, for example electronegativity والvalence electrons, in order to be able to substitute. علشان يسوي شغل المدير لازم يكون هاي المواصفات موجودة فيه. Otherwise it will produce something else, which is another phase. And we have the interstitial solid solutions. These are the interstitial solid solutions. Of course, here we have the example is copper and nickel, which we are going to look at. The first phase diagram which we are going to deal with are the copper-nickel system, where the components are the copper and nickel. And the other type of solid solution is the interstitial solid solution, which we are looking at here. You have interstitial atoms like in the carbon and the iron. Of course, there are other conditions here, that the atoms of the carbon and of the interstitial atoms have to be small enough to be able to go in the interstitial spaces that you could see. One last concept that we also need in order to go into the thrust of the phase diagram is what we refer to as the solubility limit. Remember when we explained in chapter 4 about solid solution, we said if you have a cup of tea, for example, and you are like in the liquid solution, you have hot tea, for example, without sugar there. If you add sugar into that, then it's going to go to dissolve. So this liquid which you have here can accommodate that sugar that you're adding there, the sugar that you are adding, so it dissolves. So if you add more of that sugar, it's going to dissolve again. If you add more, it's going to dissolve again up to a certain concentration. Then what happens? The liquid here is not able to accommodate any more of that sugar. It's not able to dissolve any more of that sugar. So what happens is that they are going to precipitate at the bottom here, and this is this precipitation we refer to as, once this precipitation reaches, this is what we refer to as the maximum solubility. That concentration in the liquid dissolved there of the sugar is the maximum concentration the material can handle or accommodate or dissolve, and that is the solubility limit at that temperature that we are looking at. So in the same way, so in the liquid we said it precipitates, but in the solid, of course, we said it does something else. It develops another phase. Actually, it does not do this precipitation. It develops a different phase. We have different kinds of solubility limits. Basically, solubility limit of a component in a phase is the maximum of the component that can be dissolved in it, and this is what we already said. Solubility, for example, of alcohol has unlimited solubility in water. So this is what we refer to unlimited solubility. Water and alcohol can mix up together at any rate. You can have 90% water 10% alcohol, you can have 90% alcohol, 10% water, whatever combination that you are looking at, it will not produce any other phase in the material. It will not precipitate, it will not form any other thing. So this is what we refer to as in the liquids, of course. Now we are talking about a liquid. Since we are talking about alcohol and water, this is what we refer to as unlimited solubility. While sugar, for example, as in this example that we have looked at, has limited solubility. So this, we have unlimited solubility and we have limited solubility as well. As in the case of the sugar, we also have insoluble. For example, oil is insoluble in water. So there is no solubility at all. So we refer to it as insoluble. So we have unlimited solubility, we have limited solubility, and we have insoluble as well. That is in the case of the liquids. The same concepts also apply in the solid phases as well. For example, the copper and nickel famous system, these components, which has these two components. The copper and nickel systems are soluble at any amount, and this is what we refer to as the unlimited solid solubility. You can mix copper with nickel at any amount, from 100, from 0 to 100, and from 100 to 0 of any of them. There would not be any new phase which will be forming. Of course, we will be dealing with the details of this system in the first phase diagram that we are going to cover, and why does this happen in the unlimited solid solubility. We are going to explain that as well. So the copper nickel system are unlimitedly soluble one into the other one, while, for example, the carbon in the iron has a limited solubility. Why it has limited solubility? Has limited solubility because as we add carbon to the iron, after a small amount of addition of the carbon in the iron, the phase is going to change in the material. It produces different phases basically in the material with the addition of the carbon. So this is what we refer to as the solubility limit. Now let us see how does a phase diagram looks like, very simply using the simplest water sugar system that we could be having. This is, of course, we are not going to cover the water system, the water sugar system as something that we will be using, but just for illustration to know how phase diagram looks like and how we can produce a phase diagram, for example. And in relation to the solubility limit as well, we want to also practice some things. So the phase diagram looks like this. It is on the vertical axis, it is the temperature, as you can see there. Of course, here we have in degree centigrade. Degree centigrade is what we are used to. And in the horizontal axis, you have the composition. In this case, we are having the weight percentage of sugar. So that is the composition, and that is the temperature. How do we develop the phase diagram? This is actually the solubility line. Imagine now we don't have this. Just forget about that line and let us see how this is basically the phase diagram with the solubility lines. This is what the phase diagram is. It shows the phases. Like here you have a liquid. How many phases you have? You have one. What is the phase? It's a liquid. In this region, how many phases you have? You have two, liquid and solid. What are the phases? It's liquid and solid. Of course, this is very simple, but we will go later into the different phase diagrams. It will be more involved, and you will see how we will be using that. But for now, so it consists of the axis, the phase diagram of the temperature and composition, and of the solubility lines, which shows and distinguishes the different phases at different compositions and at different temperatures. How do we develop the solubility limit? Well, basically, we can go, for example, at, let's say, we make the liquid, we will take water and start with zero composition there at 20 degrees centigrade, and then we start adding sugar to the water. We start adding, so we are increasing the composition up to 20%, 30%, 35, 40%. We add the sugar in the water until a certain specific point that we are going to reach. We will see that the water is not accommodating any more sugar, and the sugar will start to precipitate. We mark that point. Then we will go at a higher temperature. Let's say so let's say at 40 degrees centigrade. We do the same thing. We start from zero composition, about zero. Then we increase the sugar. As we increase the sugar to 40 to 30, and we will see how we are going to follow. Once we see that the precipitate forms, this is our next point. Then we start with another fresh water, 0% sugar, and we do it at 60 degrees centigrade. And from that we increase the sugar in it, until we see that precipitation happens. That's the maximum solubility of the material, and so on and so forth. So we will do it for different points. The more points that you do, the better the accuracy of the solubility limit, and then you join this line together. This is how you will be getting the solubility limit for the phase diagram. So if we want to look at this, for example, you could be asked, what is the solubility limit for the sugar water system at 20 degrees centigrade or for 30 degrees centigrade? You could just go at 20 degrees centigrade and see where it is going to intersect with the solubility limit here, and read the composition here. You will say my maximum solubility at 20 degrees centigrade is 65% by weight sugar, for example. As you can see from the phase diagram, as I already mentioned, you will have before the solubility limit, it was all liquid, and that's why you will be writing here liquid. After the solubility limit, you will know that precipitation is going to happen. So there is a solid phase that you have, and there is a liquid phase that you are having there. Now, solubility limit increases with temperature. How is that? Let's say we are at this point. At this point, how many phases do we have? Well, at this point, at that temperature, 20 degrees centigrade, and 70% by weight. So that is the temperature, and that is the weight percentage. That is the weight percentage. So we are looking at that. So if we are at that temperature and at that composition, how many phases do we have? We have two phases. We have the liquid and we have the solid. So we have solid S and liquid L, two phases. Now suppose we increase the temperature from point A, we increase the temperature from 20 degrees centigrade to basically 100 degrees centigrade. Here we are having it the other way around. We should not be doing that. So this is the temperature and this is the weight percentage. And in here also that is the temperature and that is the weight percentage. All that you don't get confused. Okay, so when we just raise the temperature, we don't change the composition. We raise the temperature from 20 degrees centigrade to 100 degrees centigrade. What happens there? Well, it has effect on the solubility of the material. Here we had solid and liquid. Now at that point we only have liquid phase, because the solubility actually is a curved line. So solubility of this increased that amount. So all the solid which is in the material is going to dissolve, and you will be having only one phase, which is the liquid. Now if you again at that temperature you increase the composition there and go to 90%, again you are going to fall in the other region with the two phase, in the regions of the two phases there again. So you can clearly see the temperature and composition, both of them actually. Changing the temperature can change the number of phases, and changing the composition also can change the number of phases that you are having. We change the temperature here, We increase the temperature, it changed the number of phases that we have. We had 2 phases here, now we have 1 phase here. Changing the composition also can change the number of phases that we could be having. This is a simple practice on the simplest phase diagram ever, just to make you aware of what phase diagrams are. This is basically what a phase diagram. Before we go into phase diagrams, again, we are just going to review what I already said about the phases. A phase must have the following characteristics in order to be termed a phase. It is a homogeneous crystal. It is homogeneous in a crystal structure or atomic arrangement, because atomic arrangement is the same meaning as the crystal structure. We have the same chemical and physical properties throughout it, so to characterize it as a phase. We have a definite interface. It has a definite interface. It has a definite boundary, basically. This is what a phase would have, and be able to mechanically separate it from the surroundings. So it can be easily separated from the surroundings. This is how we have defined the phase in the previous slides that we have.
Doctor?
Yes.
How we said that the phase should have the homogeneous structure. So why in the substitutional microstructure is it still homogeneous since we have other atoms?
Homogeneous, it could be with one type, with one atom. It could be with different atoms, but they are homogeneously dispersed in the material, isn't it? So that is homogeneous also. Yani homogeneous does not mean you have only one single type of atoms there. Homogeneous, it could mean also that you have a dispersion of different atoms in the same material, and of different atoms but dispersed evenly and equally in the material. This is what homogeneous means, صح?
تمام دكتور.
So we have a homogeneous structure, crystal structure, atomic arrangement in the material. This is what we need to see in a phase. One thing also, so that you don't confuse, and also we shed light on that, do not confuse the phase with a grain. So when we talk about a grain, when we have a grain, so this is, let's say, a polycrystalline material, looks like this. This is a polycrystalline material. This is a grain. This is a grain. This is a grain. This is another grain. This could be, يعني, these are grains, but these are a single grain can have only one type of crystal structure. A phase in the material, let's make it bigger. So these are grains, but we could be having a phase there, another phase, and these are different grains as well. And we have another phase here. How will I draw that? But in this phase, which is different, you will be having different grains as well. Yani this is one grain, this is one phase. Let me do it in another color. In color. Let's say this is another phase. This is the material itself has a phase. This is one phase, and it has different grains. This is a grain. This is a grain. This is a grain. This is a grain. These are all grains. This is one other. This is one phase. This is another phase. This phase also has different grains in it. So what I want to say is that don't confuse between the grain and the phase. A phase can have many grains in it. This is the second phase, so this is another phase different than that one, has different grains in it. But a grain itself, this is one grain, it will not have different phases in it, because a grain itself has one crystal structure type only. Again, here also, this grain cannot have two phases in it. It has only one phase in it, each grain. But a phase, this is a phase, can have different grains in it. This is a phase, can have different grains in it. And this is what I'm saying. A single phase material may contain many grains. However, a single grain consists of only one phase. So a phase may contain one or more grain components in it. Also, what we mean by phase, for example, in a pure material, phases, for example, that you have considered before and seen before, and water, for example. Water has different phases. Like there is the ice, there is the water, and there is the steam. These are different phases of water. In the steels, we have in the solid metals, for example, in the metals specifically, we have also different phases there as well. In the same way that we have talked about pure materials like the water. When we have a single phase in the material, we normally refer to it as homogeneous structure. Homogeneous, يعني you have a single phase. For example, this is not homogeneous now. You have two phases coexisting in the material. This is not homogeneous. This is what we refer to as heterogeneous material. Heterogeneous systems are systems which have two or more crystal structure types. Two or more phases in the material are called heterogeneous systems or heterogeneous microstructures. When the material consists of only one phase, one type of crystal structure only, we refer to that as homogeneous structure or configuration. One more point before we go in the phase diagrams. Again, we have 10 minutes more to go. We want to just shed light on the microstructure of the material. Now, we said before that we can use the phase diagram in order to predict the microstructure of the material, and from the microstructure of the material, why is this happening? Who's asking for control? There are people who are asking for control on my computer. Please stop doing that. Okay, so again, we talked about here. We said that the structure of the material, if we can predict the structure of the material, then we can predict the properties of the material also. So if we can use the phase diagram and the heat treatment route or the heat treatment history to predict what the structure is, then we can predict also the properties of the material. So this is what we say. Now, how is it that the different how is it that the microstructure of the material we can see? Of course, it could be seen by optical or electron microscope techniques that we already covered in chapter 4. Using appropriate polishing and etching, we can see what the microstructure is, and therefore we can predict the properties of the material. If we heat treat the material, or there is a heat treatment history, and we have the temperature and the composition of the material, then we can predict what the structure is of the material using the phase diagram. We can see it also using these means there. The microstructure of an alloy is characterized basically by certain things. Characterized يعني شنو؟ يعني different microstructure shapes or types can produce for you different characteristics, give different properties of the material. The different microstructures, like the number of phases which are present. We already saw that. We said at the beginning of the chapter, we said we can use the phase diagram, or of course, in addition to the history of heat treatment, we can use the phase diagram therefore as a tool to predict predict the number of phases that we are going to have. Number of phases يعني شنو? Well, if you have a single phase material, let's say you have one single phase in the material, or you have multiple phases in the material, not only one phase, you have different phases coexisting in the material. And let's say this is one phase, so the other phases are in that phase. Let's say you have مثلا color right here. This is another phase there in the material with different grains as well. Okay, and this is color, this is a third phase in the material, and it has different things there as well. This is a homogeneous system. It has a single phase. This is a heterogeneous system which has different phases. This is one phase, this is another phase, and the third one which is surrounding both actually. This is called heterogeneous system. If you have one crystal structure, if you have one phase in the material, of course the properties, suppose for example this has a BCC crystal structure. The BCC crystal structure has certain strength, certain specific mechanical properties, the BCC. And on the other hand, here in the other one, you have three different phases occurring in the material. Suppose this is the BCC also, this is an FCC, and that is an martensite, which is the BCT crystal structure type, which we are going to cover later. Okay, so we have different phases happening in the material. Each phase, each crystal has different crystal structure, which means that each phase has different properties, different strength, different hardness. Would the behavior of the material be the same? Of course not, because you have different phases in them. So the number of phases, as we are mentioning there, when the number of phases there is an important thing that if we can predict, it's good to predict the properties of the material. This is what characterizes the microstructure. Another thing, their proportions. How much, if it is a single phase, then it is 100% of that. If it is if it is heterogeneous system, then how much do we have of this phase, and how much do we have of this phase, and how much do we have of this phase? And suppose this is the hardest phase. Let's say this is the martensite, for example. Martensite is the hardest phase ever in the steels. And this is, let's say this is bayanite. This is bayanite, and this is the ferrite phase, the alpha phase. The alpha is the softest phase. So if we have, for example, let's say 95% is the ferrite, and 1% is the bayanite, and 4% is the martensite. Or in the other case, let's say we have 50% ferrite, and 5% bayanite, and 45% martensite. Would the properties be different? Of course it will be different, because the addition of that martensite in the material makes the material very hard. So therefore the proportions of the phases is also important, how much of each we have. And this is something that we can get from the phase diagram, from that tool that we talked about. So that is very important actually. If we know how much of the phases are there, the proportions, the volume fractions, later we are going to see that, then it is important to predict the behavior of the material, the mechanical properties of the material. Not only the number of phases and their proportions, but also their compositions as well. Yani the composition, although this is a phase, what the composition itself, let's say, it is let's say this is, for example, ferrite, or this is martensite by itself. This is a BCT crystal structure. Well, it has a certain composition. if we increase the composition of that solute that we are adding, would it change the mechanical properties of it? Indefinitely, it's going to do that. Yani the addition of more carbon in it, would it change if there is no change in the crystal structure, would it change the property? Of course, it's going to change. The addition of more alloying element, would it change the properties of the material? Obviously, it's going to change the properties of the material. The same thing here, if you have in a heterogeneous system, that's martensite, that's bayanite, and that's ferrite. The more carbon in each one of them, it changes. So at lower carbon content, their behavior is a little bit weaker. At higher carbon content, their behavior is higher. So also, in addition to these that we have mentioned, the composition as well is very important. The composition of each phase, the composition is very important. Composition. I did not put my pen on this my taking time to write. So the composition is very important. Part of characterizing the microstructure of the material as well. In addition to that, the manner in which they are distributed, manner by which they are distributed, يعني شلون they are distributed basically. Like this is what you could see. This is a heterogeneous system here. You have the beta phase, you have the alpha phase, so that it consists of different aluminum copper alloy basically, and it has different alloys here. But let me continue talking about the manner, the way that they are distributed also is an important aspect which characterizes also the material microstructure. Let us see these figures here. As we said, the number of phases which are present are important. This is a single phase material, as you can see here. It has different grains, but this is single phase. So this is, let's say, this is a ferrite phase. In here, this is steel basically. This is the ferrite phase. This is a second phase. This is another microstructure. We have two different phases coexisting. The ferrite phase, which is the white one, and the black, it is what we refer to as the martensitic structure. This is another another microstructure. The arrangement are different basically. We'll come to this in a minute. So what we answer normally using the phase diagram, the number of phases which are present, how many phases are present, what are the phases. Of course, it differs if it is ferrite and martensite, or if it is bayanite and martensite. Each one has different properties, so that differs as well. The composition of each phase, as I already mentioned in the 2 minutes before, the proportion of each phase, how much of each phase is there, is an important aspect which characterizes the material. And then we also said the way or the manner by which they are distributed or arranged. And this is what I want to say. You have different arrangements there, and you have some examples here as well. The different phases. For example, you have bulky distributions of the martensite in the ferrite, separated islands, you can call those. You have the needle-like, يعني شنو needle-like? Needle-like, it's like needle-like, let's go fast. Needle-like is, let's go to the 10 option. Needle-like is like this. This is a needle-like, like these. These are needle-like. You have two phases. This is one phase, and this is the other phase. Very sharp and straight, like it looks like needles there. This is what we refer to as needle-like microstructure there. So this is what we are saying. Now,
time is up.
Yeah, 2 minutes only. We're going to continue for another 2 minutes. We have the islands, which could be continuous and which could be separated. These are the island types, as you could see. The difference in the shape of the microstructure changes the property of the material. And keeping everything else constant, just the shape of the microstructure there changes the property of the material as well. These are the separated islands, but you could also have non-separated islands. يعني شنو؟ يعني the islands could be You could be having continuous islands. Yani this is a phase. You could be having islands like this, and you could see them close to each other. So we refer to that as continuous islands there. So that they are continuous. This also changes the mechanical properties of the material, because this continuity actually causes the restricts actually the plastic deformation in certain is the property of the material as well. You could be having a spherical واضح يعني you would be having you could يعني ممكن يكون fine dispersions or spherical. Let's say spherical, يعني you know, this is the microstructure. You could be having spherical microstructure like this. This is the most ductile actually dispersion, which can produce the most ductile property of the material. You could be having very fine dispersions there, like that, very fine points, dots of the microstructure there. This is also another manner by which the microstructure could be dispersed there. You could be having lamellar, like in the for example in the perlite structure. That lamellar is important, which we are going to see it. Lamellar, which is in different grains, you could be having lamellar configuration like that. That also gives different properties of the material. We will be looking at that as well. You could be having banded microstructure. Banded, and you could be having like the phase having bands actually like this. This is a phase, and this is another phase here, and in between other phases, this is a phase. You could be having banded type of microstructure there. Each of these basically has different effects, has effect basically on the microstructure. You could be having coarse or bulky, globular networking. This is an example of networking. You can see like there is a network going on between the microstructure. In the second phase, it's like a network distribution there. You could be having fine network and coarse network as well. The shape of the microstructure, this is what I want to say from all this. The shape of the microstructure, the manner by which the phases are distributed or arranged in the microstructure also is an important aspect which characterizes the microstructure and changes the mechanical properties of the material, keeping everything else constant. This is what I wanted to say. Time is up. Yes, time is up. I am ending the lecture at this point. We will next time talk about go in the thrust of the phase diagram. Any questions before you leave? ما هذا وايد يعني الناس زعلانين ايش فيكم ما تسألون. I will stop the recording so that